Assalamualaikum Dr. Ainul. We are from Group 5. We will be presenting our project titled RAM Study for Gas Processing Plant for the course Asset Reliability, Availability and Maintainability. My name is Muhammad Rasaikal, and together with my teammates Muhammad Syafiq Ilmi, Fahna Sakina, Muhammad Lukman and Muhammad Rakib, we have conducted a comprehensive analysis of the plant's performance. So in this presentation, we will evaluate the system in terms of their reliability, availability and maintainability, identify critical equipment affecting performance and propose improvement to achieve a target availability of 99%. So now let's begin with the introduction of our study.
Assalamualaikum Dr. Ainul. Our group will be presenting a project title called RAM Study for a Gas Processing Plant. We are from Group 5. This project focuses on the reliability and availability for analysis of a gas processing plant. In such plant, high reliability and availability are very important because the system operates continuously. Any failure in the system can lead to the production loss and increase the operational cost. To analyze this, RAM analysis is used. RAM is stand for the reliability, availability, and maintainability. It helps to evaluate the overall system and identify the weakness in the system. In this study, the plant availability is analyzed over a 5-year operational period. For the analysis, Weibo++ software is used to model failure and repair data, while BlockSim is used to simulate the system using reliability block diagram or RBD model. So, the objective of this study or this project, first to establish the assumption of for the RAM analysis. Second, to evaluate the average plant availability. Third, to identify the critical equipment in the system. And finally, to propose strategy to achieve the target of 99% availability. Thank you.
Assalamualaikum Doctor, I'm Fadlin and in this group I'm responsible in handling the Weibo++ software. So for this software, I did the analysis for both failure data as well as the repair data. For failure data, it will be used for reliability analysis, and for repair data, it will be used for maintainability. Okay, starting for the failure data analysis, what I did firstly is that I convert all the days data into a cumulative days. So this is to ensure that we will take the actual duration that the component has failed and not only the interval. Okay, so this is the screenshot of the failure data analysis that I did in Weibo. As you can see, I have pasted all the cumulative days that I convert into here and the middle column there. You can see that I set all the row as failure except the last one, which I set it as N. So this is to indicate that I treat this data as a failure truncated and not time truncated. So using this table, I was able to calculate the important parameters, and with this beta value, I managed to determine the pattern failure over time. So this is the screenshot of the pattern failure over time. As you can see in the left side, the component experience an increasing failure rate where the data actually increases exponentially with time. And in the right side, the component actually experience a decreasing failure rate where the data is becoming more constant over time. Moving on to the repair data analysis. So for this repair data, the time that we have obtained is already independent and it's complete by itself. So we do not need to convert it to cumulative days like what we did with failure data analysis. So with this data, we can directly copy paste it into Weibo. So this is the screenshot for the repair data that I did in Weibo++. As you can see, I have pasted all the data directly into this, and then the reason why I use Weibo++ is for me to determine which distribution fits the best for this data, and this can be easily done using the distribution wizard. So for example, over here, this component, which is compressor, the best distribution that fits is exponential. So after I've completed all this, both failure and also repair data, I publish it into the Weibo, and then it is used directly for the next part, which is BlockSim. That's all from me. Thank you.
Hello, my name is Muhammad Lukman, and for this presentation, I will be presenting on the RBD modeling of this project of ours. So first thing first, what we have here is the overall system that we have modeled. And within the system, there are 7 smaller subsystems within it. And in the next few slides, we would be reviewing each of these subsystems and some of the assumptions that we have made along the way. But for this particular system, the condensate and water treatment unit, the NGL unit, and lastly, the sales gas unit, all 3 of these blocks are modeled to be unable to fail, as there are no data provided in the Excel, which supports all 3 units of these. So let's look into each of the subsystems one by one. So first thing first, let's look at the MP separation unit. It's pretty standard. All of the blocks are modeled to be able to fail, as there are data supporting each of the blocks in the Excel. So the system consists of the 3-phase separator, the suction drum, booster compressor, the driver motor, aftercooler, and lastly the discharge drum. So moving on to the HP separation unit. So this unit, it only consists of 2 blocks, which is the slug catcher and the 3-phase separator units. And both of these units, they are deemed to be able to fail, as there are data supporting them provided. So moving on to the feed gas compression unit. So there are 7 blocks here, namely there are feed gas separator, the suction drum, feed gas compressor, the driver turbine, aftercooler, trim cooler, and the discharge drum. And similar to the first 2 units that I've shown, so all of these blocks, they are modeled to be able to fail, as there are data supporting them being provided. So now let us look at the acid gas removal units, and here things start to look a bit different. So the first block, which is the sour gas knockout drum, it was deemed to be unable to fail, as there is no data supporting them being provided. And the filter separated there, it utilizes the separator's data. And lastly, the absorber block, it of course utilizes the absorber's data provided in the Excel. Now let us have a look at the amine regeneration unit. So the first block there, which is the rich amine flash drum, it was deemed to be unable to fail, as there is no data. Same thing with the sulfur recovery and tail gas treatment unit. Both of them are deemed to be unable to fail, as there are no data for them. And the lean amine cooler, it uses the trim cooler's data and distribution. And same thing with lean amine exchanger, it uses exchanges data and distribution. And for the reflux pumps here, it was modeled using multiple blocks. With each pumps, there are 2 pumps, with each pumps operating at 100% capacity. But for the lean amine pumps, it was also modeled with multiple blocks, but each of these pumps, they are only operating at half capacity, meaning at 50%. So moving on to the dehydration unit. So the first block we have here is the sweet gas cooler. It utilizes the trim cooler's data. And the feed gas pre-chiller, it also uses the chiller's data. And for the molecular sieve beds, it was modeled using the standby container construct, which basically allows blocks to be modeled whether on standby or active. So in this case, the online block is set to be active, meanwhile the regenerated block is set to be on standby. So moving on to the last part of this RBD modeling, which is the NGL unit. So all of the blocks here are modeled to be able to fail. And for the turbo expander with JT bypass, again, it utilizes the standby container construct. And in this case, turbo expander is set to be active, meanwhile the JT valve is set to be on standby. So in the case of the turbo expander failing, the container would switch to the JT valve. Yeah. So that's all for the RBD modeling. So moving on to the next part of the presentation.
Okay, now I will explain the key assumptions used in this RAM analysis. First, the plant is assumed to operate under continuous operation 24 hours per day throughout the entire 5-year simulation period. In terms of maintenance condition, we assume that repair activities start immediately after a failure occurs, with no delay in spare part availability, and maintenance resources are always available. This means there are no logistical or manpower constraints affecting repair time. Additionally, preventive maintenance is not considered in this model, only corrective maintenance after failure is included. For model limitation, environmental and human factors are neglected, allowing the analysis to focus purely on equipment reliability. And finally, for failure modeling, all failures are assumed to follow a Weibull distribution, and importantly, failures are independent, meaning the failure of one component does not directly cause another to fail. This assumption simplify the model and allow us to focus on inherent reliability characteristic of the system. Next, I will continue present the average availability result of the plant over 5 years period. Based on the block sim analysis, the overall plant availability is 96.38%, which means the plant is operational most of the time, but still experience about 3.62 downtime. In terms of operating time, the plant achieved approximately 42,218 hours of uptime, with about 1,581 hours of total downtime over the 5 years. Now, looking at the subsystem performance, the generation unit shows the highest availability at 99.84%, followed by the HP separation unit and NGL recovery unit, both with a very high performance. On the other hand, the amine regeneration unit has the lowest availability at 98.75%, making it the main contributor to the system downtime. The feed gas compression and MP compression unit also show slightly lower availability due to their dependence on critical equipment. Overall, even though most subsystems perform well, the combined effect of this lower performing unit reduced the total plant availability below the target of 99%. This highlights that improving a few critical subsystems can significantly enhance the overall plant performance.
Assalamualaikum, Doctor. My name is Shafiq Hilmi and I'm responsible for the identification of critical equipment based on block sim reliability analysis. So, from the analysis, the bin plant availability is 69.38%, which is below the target of 99%. This indicates that the system is not performing at the desired reliability level and improvement are needed. Based on the result, we found that only a few equipment contribute most of the total downtime. The highest contribute are the feed gas compressor, residue gas compressor, expander compressor, and a reflux drum. These equipment have the highest value of RSFCI and RSDTCI, meaning they contribute the most system failure and downtime. It is also important to note that most of these are rotating equipment, especially compressor, which operate continuously and more prone to be failure. Therefore, these components are identified as a critical equipment and should be prioritized for reliability improvement in order to increase the overall plant availability. Okay, next I will explain the critical equipment ranking, which is have a top 3 critical equipment. Number 1, the feed gas compressor is ranked first with 11.91% for RSFCI and 8.59% for RSDTCI. This means it has the highest impact on the system failure and significantly contribute to the downtime. Number 2 is residue gas compressor, show almost the same contribution, indicating that compression system are the main bottleneck in the plant. Number 3 is the expander compressor. The expander compressor show almost the same contribution, indicating that compression system are the main bottleneck in the expander compression also has a high contribution as it is part of the NGL recovery system, which is critical for plant operation. Now, looking at the overall ranking, this slide show the critical equipment identified based on the block sim analysis. The ranking determined based on the percentage contribution to the system failure, which is FCI, and total downtime, which is RSDTCI. The equipment with higher value are considered more critical. In addition, as number 4, you can see the reflux drum, even though it's not a rotating equipment, that show the highest downtime contribution. This indicate that when it fails, it take a longer time to recover. The reason why this equipment are critical is because they are located in a series configuration where failure of one unit can cause a total plant shutdown. Furthermore, the compressor operate continuously under high load, which will increase their tendency to fail. Therefore, it can be concluded that the rotating equipment, especially compressor, dominate the system failure and downtime. ensured, and it should be prioritized for the improvement. Thank you.
My name is Muhammad Rakib. I will be presenting on the improvement strategy. To start, we must look at our overall plant availability before any improvements. On the screen, you can see the initial reliability block diagram of the plant. This was built using block sim. Next to it is the baseline result table. We ran the simulation on this original configuration. The result showed an overall plant availability of 96.38%. This falls short of our strict 99% target. Because of this gap, we had to develop a comprehensive improvement strategy. Our primary goal was to close this 2.61% availability gap to exceed the 99% target. For this scenario, we assumed there were no budget or space limitations. To reach this goal, we developed a two-part improvement strategy. Our first approach was to introduce structural redundancy. This means adding backup equipment to eliminate severe single points of failure. Our second approach was to optimize our maintenance protocols to improve equipment reliability and reduce repair times. Okay. On this slide, the table details the engineering changes we applied to our critical equipment to execute our strategy. For our first structural redundancy, you can see in the far right column where we added standby units. We implemented redundancy for the reflux drum, suction drum, the driver units, and most importantly, our major gas compressors. Our second approach, maintenance optimization, the middle columns show where we adjust our simulation parameters. We increase the MTBF for all filters and major rotating equipment to reflect a new proactive maintenance program. Simultaneously, we reduce the MTTR for our drums, coolers, and the regenerator to represent a faster localized spare parts strategy. By combining these specific equipment upgrades, we systematically targeted and eliminated the plant's major bottlenecks. Okay, next, this slide shows our step-by-step progress. On the left side, the table details the actions we took across 14 simulation cases. On the right side, the line graph visualize our growth. As you can see, we started with our baseline in case 2. The initial plant availability was 96.38%. We then began applying our improvements one by one. The graph demonstrates steady growth as we implemented each phases. For example, in case 3, we optimized the major compressors. In case 5, improving the pump gave us another significant boost. Every single action we took successfully increased the overall reliability of the system. By the time we apply our final upgrades to the gas filters in case 14, we reached our goal. The result shows the plant reached 99.23% availability. This step-by-step data proves our improvement strategy was highly effective. Bring us to our final optimized model and conclusion. On the screen, you can see the improved Block C model. Our strict project target was to reach 99% overall availability. Through our step-by-step strategy, our final achieved result is 99.23%. This proof our engineering decisions were successful, adding structural redundancy, eliminate the severe plant bottlenecks. Furthermore, our maintenance optimization greatly reduced the downtime for major equipment. We can confidently conclude that the gas processing plant now meets all production and reliability requirements. Okay, thank you. That's all from me.